So let's start with the part E of question number 7. Alanine. Okay, we got this structural formula of alanine. Reacts with methanol to form ester G under certain conditions. The proton hydrogen NMR spectrum of G dissolved in D2O. Okay, it's dissolved in D2O. Is shown in figure 7.3. Okay, let me do this easier for you. See, there is a one carbon. If we draw the alanines, there is a one carbon, it has a hydrogen, and on other side there is a CH3, and this side we has a C double bond OH, and here we have NH2, right? So if you look at this structure, how many different kinds of hydrogen this structure has? You see, 1, 2, 3, 4. There are 4 types of hydrogen, right? But if you see, here we are getting 3 signals because at a 0, whatever the signal we got, that signal is of solvent, right? So we are getting 3 signals. And as they have told you that it is dissolved in D2O, so we can easily figure out that the NH2, the signal of these hydrogens is missing due to D2O as D displaces hydrogen. Is this understandable to all of you? Okay. Now, if you look closely to them, you will find this one a singlet, this one a quartet, and this one a doublet. Is this understandable? Yes. Now, as it's a singlet, it's a quartet, it's a singlet, and it's a doublet. So what we conclude from here, that no hydrogen on adjacent carbon. Doublet means one hydrogen on adjacent carbon, and quartet means 3 hydrogens on adjacent carbon. Is this clear? Now, let's do the thing. If I'm highlighting this with the green, so look at the hydrogen that the neighboring carbon has 3 hydrogens. So isn't it this hydrogen? Is this clear? Now, a doublet. if we see this is a doublet, which means the neighboring carbon has a two hydrogens. Sorry, one hydrogen. So isn't it this is due to these three hydrogens as their neighboring carbon has only one hydrogen. Is this clear to all of you? Yeah, they have a three hydrogen, but the splitting pattern tells us that how many hydrogens are on the neighboring carbon. So as a doublet, it's a doublet, so it means that their neighboring carbon has a three hydrogens. Sorry, as it's a doublet, so it means their neighboring carbon has a one hydrogen. So this doublet is a signal of a three hydrogens because on their neighboring carbon there is a one hydrogen. Okay, but the interesting thing over here, basically this spectrum is of G, right? So, and G has one CH3 over here. So it means there is instead of OH, if I'll make here a CH3. So see, there is a no hydrogen on neighboring carbon. So it means this signal, this one, is of these three hydrogen because as there is no neighbor carbon as well and there is a no hydrogen on it, so that's why we are going to get a singlet of this one. Is it clear now? Yes, Shahan, it's a proton NMR. Carbonyl carbon has no hydrogen. We always get the signal for a hydrogen. See, I have highlighted hydrogen. I didn't highlight a single carbon on it. It's a proton NMR. Yes, so it has a singlet because these hydrogens are bonded to a carbon and neighbor to that carbon, there is a no carbon. Or you can say that neighbor to that carbon, if there is a carbon, but that carbon has a no hydrogen, that's why we are getting singlet. Till here, is this clear to all of you? So we have figured out all of the three types of the signals, right? Now, they have given us this information, the table they have provided us, and they are asking us complete table 7.2 for the proton NMR of a spectrum G, splitting pattern. So at 1.4, we have identified that it's doublet. And then it's around 3.5, it's singlet. And at 4, it's quartet, right? So doublet, singlet, and quartet. Is this clear? Now, number of protons responsible for the peak. So the peak, which is a doublet, are due to three hydrogens, right? These three. This singlet is due to these three hydrogens. And this quartet is due to one hydrogen, this one, right? So 3, 3, and 1. So I'm going to write 3, 3, and 1. Is this clear? Now, in the next part, they are asking number of protons on the adjacent carbon. So as a doublet, so it means there is a one proton on the adjacent carbon. Singlet means zero proton on the adjacent carbon, and quartet means three protons on adjacent carbon. Is this clear? Now, part 2. The proton NMR of spectrum G dissolved in CdCl3 is obtained. See over here. They have this spectrum is obtained in D2O, and that's why we have decided that these two hydrogen signal is missing, as D displaces this hydrogen and instead it becomes Nd2, and that's why the signal disappear. Where is a triplet, Mahavi? See, the pink one is a singlet, the brown one is a doublet, and the green one is a quartet. There is no triplet over here, if you see. So if it's a triplet, so it means adjacent carbon has a two hydrogens or two protons. I have uploaded the recording of proton NMR in the playlist. You guys can watch over there if you have any confusion in proton NMR. Okay. Okay. So describe the difference observed between this spectrum and the proton NMR spectrum in D2O. So as there is CdCl3, so that in CdCl3 the NH2 signal would be there because no D is going to displace the hydrogens. So I will write. So if there is a CdCl3, if NH2 signal would be there, so we are getting one more peak. So there is one more peak of hydrogen of NH2 group in CdCl3 as in D2O, the D displaces H in NH2. Is this clear to all of you? If any one of you has any confusion till here, please ask. Okay. Now, question number 8A. Complete table 8.1 by placing one tick in each row to indicate the sign of each type of energy change under standard condition. Lattice energy. If you recall, the lattice energy is the energy change when gaseous ions turns into solid. So when the gas turns into solid, the energy would release or the energy would absorb, or it can be either. Yes. The gaseous ions turning into solid, so it means it's a formation of a bond, and whenever the formation of a bond, the energy is always released. So if the energy is always released, yes, very good, Shahan, very good, Ahmed. So it means that it is always going to be negative. Then enthalpy change of hydration. For hydration, if you recall, when the gaseous ions turns into aqueous, so again see gaseous from is turning into aqueous. So in aqueous, when it dissolves in water, it bonds with the water and formation of bond is exothermic. So again, the energy is going to release only. So it is going to be always negative. Then the enthalpy change of a solution. So enthalpy change of a solution when a solid dissolves to form aqueous. So in this, bonds are broken and bonds are formed. So when the bonds are broken, energy is absorbed, and when the bonds are formed, energy is released. So it vary. If the bonds broken, when the bonds are broken, more energy is released, so it becomes endothermic, so it is positive. And when the bonds forms are stronger, so more energy is released, so as a result, it becomes exothermic or a negative. So we can say that it can be either negative or positive. Is this clear to all of you? This is for this one solution. Okay. Now define the enthalpy change of hydration. So you guys must remember the definitions. So we can write that it is the energy change when 1 mole of gaseous ions dissolve in water to form very dilute solution. There is no need to write standard conditions because they didn't ask you for the standard enthalpy change, right? Very dilute solution. Okay. Now, C part. Table 8.2 shows various energy changes which can be used in the following question. Okay. Atomization of calcium. First ionization energy of calcium. Second ionization energy of calcium. Atomization of bromine. Bond energy of bromine. And if you recall, bond energy, as it's a diatomic, so it's divided by 2, give me the atomization as well. No, not for bromine because bromine is a liquid. Sorry. For a gaseous, we would do this. Standard enthalpy change of solution of calcium bromide. Okay. So enthalpy change of solution of CaBr2. Enthalpy change of formation of calcium bromide. Okay. Hydration of calcium ion and hydration. Okay. Electron affinity. First electron affinity of bromine and first ionization energy of bromine. So see, here examiner tricked you. Let me show you how. As they have asked you calcium bromide. So if you look for the oxidation states of these elements in calcium bromide, so its calcium is 2 plus and bromide is -1 and there are 2 bromide. So as it's a -1, so this is not needed. Is this clear? Okay. Now further, whichever value is going to be used, we are going for a bromide, we are going to make it twice, like first electron affinity and atomization because there are 2 bromines. Now, what they are saying in part 1, select and use relevant data from table 8.2 to calculate the lattice energy of calcium bromide. It may be helpful to draw the labeled energy cycle. Show your calculation. Okay. If you recall the mathematical expression for the lattice energy, so the lattice energy is equals to enthalpy change of formation minus sum of enthalpy change of atomization plus sum of enthalpy change of ionization if the atom has more than one oxidation state. No, I think we don't use. Let me first write the expression, then I'll tell you, okay? And then the sum of enthalpy change of electron affinities if there are more than one electron affinities. Just guys, give me a minute, please. Okay, so now if we go for enthalpy change of formation for calcium bromide, it's over here, minus 682.8. So minus 682.8 minus atomization, as both the elements must be atomized. So we need the atomization of both of them. Yes, Maham, we don't need the atomization. We are given with the atomization of bromine, so there is no need for a bond energy. So see here, it's just to confuse the students because you are given with this thing, so there is no need to use bond energy. If atomization is not given, then you have to use the bond energy. And as I have told you, it's we have to twice it. So, and we need the atomization of calcium as well. So it's 178.2 and it's 119.9. So 178.2 plus 2 times 111.9 because there are 2 moles of bromine. Then ionization energies. As you see, calcium is plus 2. So both the ionization energies would be needed. So 590 plus 1145. So 590 plus 1145. And then the electron affinities. Bromine is -1. So only first electron affinity, but there are 2 moles. So that's why you have to make it twice as well. So then plus 2 times minus 324.6. So now you got the values in the expression. Now you will solve it and you will get the answer. Can anyone solve it and tell the answer, please? And if any one of you has any confusion, please ask. Okay. Asif is getting minus 2170.6. So minus 2170.6. Okay. Mariam, please check. It's not 21,706. It's 2170.6. Now, part 2. Select and use relevant data from table 8.2 and your answer to C1, that is the lattice energy of calcium bromide, to calculate the standard enthalpy change of hydration of bromide. It may be helpful to draw a labeled energy cycle if you were not able to. Okay, so we got that value, so we don't use this. Okay, sure, you're working. So if you recall, they have given you the enthalpy change of solution and we have calculated the lattice energy. So if I make the equation, there is a gaseous sign And there are two gaseous ions over here, and they form solid calcium bromide. So it is going to be lattice energy, right? When the gaseous ions forms ionic solid, it's the lattice energy, and its value we know, minus 2170.6. That's what we have calculated. Is this clear? Now, when this solid dissolves in water, we get aqueous calcium bromide. So that is going to be enthalpy change of solution, and they have given us the enthalpy change of solution of calcium bromide, which is minus 682.8. Is this clear? Okay. When we move an arrow from here, so we got the hydration of calcium and twice of hydration of bromide, because the gaseous ions are turning into solid, into aqueous. So the hydration of calcium is given over here, which is minus 1579, right? So minus 1579 is the hydration of calcium plus 2x, because we don't know and we have to find the value of x. Now, if you look at the arrows, there is a one root this, because these two arrows are in a one direction and this is the in the opposite direction. So if I make the mathematical expression, it would be like this: minus 1579 plus 2x is equals to minus 2170.6 plus minus 682.8. Now, if I have to calculate the x would be equals to minus 2170.6 plus minus 682.8, and that minus turns into plus when I move to the opposite side of is equals to, or the expression, and then divide by 2. It's 103.1. What is 103.1? Okay, thank you. It's 103.1. Sorry. My bad. Thank you, Ahmed. It's 103.1. So 103.1. So plus 103.1. Can anyone calculate it and tell me the answer, please? Okay, if you don't, remember this diagram, and if you find difficult, this diagram would be difficult for you. So then you have to remember this expression, that the enthalpy change of sum of enthalpy change of hydration, because there are two ions. So the positive ion have an individual hydration and the negative ion has an individual hydration, is equals to lattice energy plus enthalpy change of solution. So in this case, we have a hydration of calcium ions plus twice of enthalpy change of hydration of bromide ions is equals to lattice energy plus enthalpy change of solution. And that's what we make it 2x over here. Is it clear, Miriam? Okay. So you guys are getting minus 244.25. Can Azif and Maham and Shahan, can you guys recheck your answer, please? 2170.6 minus 103.1 minus 15. Yeah, it's 244.5. Okay, that's fine. 244.25. And it's in minus. Okay. Now, third part, the enthalpy change of hydration of bromide ion is more negative than the enthalpy change of hydration of iodide ion. Explain your answer. So yes, we know when you look in the periodic table, iodine is below bromine. So the size of bromide is if this much, then the size of iodide ion must be bigger. And both have a same charge that is -1. So the charge density of iodide is lower. And if the charge density of iodine is lower, so there would be a lesser force of attraction, right? Or you can uh, explain it in terms of bromide ion as well, that bromide ion has a smaller radius, but the same charge as iodide. So the stronger attract forces between the bromide ion and the water molecules, because in hydration, they dissolves in water, right? So bromide ion has a smaller size than iodine. Hence, the forces of attraction between bromide ion and water molecules are stronger. Is this clear to all of you? So here we have ended the paper, and in the next class tomorrow, it will be at 9 p.m. PST. We are going to start a new paper. Okay. So see you everyone in the next class. Take care. Allah Hafiz. I will share in the group. Okay, Shahan?